This is lesson 7.2, diagonalization. And so that's what this lesson is all about. We're going to be looking at diagonal matrices. How do we know if a matrix is diagonalizable? And then look at some properties about diagonal matrices, especially related to eigenvalues and eigenvectors. So that's what's in store for this lesson. So let's start off with a definition for diagonalizable matrices. It says an n by n matrix A is diagonalizable when A is similar to a diagonal matrix. That is, A is diagonalizable when there exists an invertible matrix P such that P inverse times A times P is a diagonal matrix. And we've certainly seen this expression before. So basically all this is saying is that if I have a matrix, a square matrix of order n, and I want to know if it's diagonalizable, I have to be able to find another matrix P that is invertible that would make this expression or that when applied to this expression would be a diagonal matrix itself, okay? And then there's kind of a follow-up theorem to this, and we'll take a look at some examples, but the follow-up theorem simply says that if A and B are similar matrices, then they have the same eigenvalues, okay? So let's just take a look at a couple examples that address both the definition and the theorem. So the first one is just really pulling an example we did in the last lesson in 7.1 that was pulled from the previous lesson, 6.4. And so this is the one where we had matrix A, we had found matrix P, and again, if we just simply plug it into the expression P inverse times A times P, we get a diagonal matrix. And so by that definition, because that expression is a diagonal matrix, we know that A is diagonalizable. So that's all that definition says. As far as the theorem goes, again, it says if A and B are similar, they have the same eigenvalues. So in our next example, we have two similar matrices, A and D, and we are to find the eigenvalues of A. Now, obviously, we could go and just directly find the eigenvalues of A using the process of the determinant of lambda I minus A and all of that. But in this case, because we know A and D are similar, and D is a diagonal matrix, we know that the eigenvalues for D are, in fact, let me just write this down. So D is a diagonal matrix, right? And therefore, we know that its eigenvalues, so its eigenvalues, are given by the entries on its main diagonal. So in this case, it's going to be lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. Those are the eigenvalues for D. And because A is similar to D, A will have the exact same eigenvalues. So this would also be for A, because again, it's similar to D. So it's just a way to quickly find eigenvalues if you would happen to know that they're similar, and if one of the matrices is easier to find the eigenvalues for than the other, you could do an indirect way like that. All right, well, moving on. Another theorem, the condition for diagonalization. It says an n by n matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. All right, so if I have a 3 by 3 matrix, I have to have 3 linearly independent eigenvectors for A to be diagonalizable. And just note, for diagonalizable matrices, the columns of P consist of n linearly independent eigenvectors. I kind of briefly mentioned this in the last lesson, but once you know those eigenvectors, if you use those as columns to create a matrix, that matrix is P. All right, so again, nothing that we have to do for this, but this was the one that we just looked at from example 2. We didn't find the eigenvectors, but if we had, we would find that for lambda 1 equaling 1, the eigenvector is 1, 1, 1. For lambda 2, 0, 1, 1. For lambda 3, 0, 1, 2. Okay? So we could obviously go through and find those eigenvectors, but those would be the eigenvectors. And therefore, again, by this theorem, P is just simply those 3 eigenvectors as columns in the matrix. All right, so finally, just some steps for finding diagonalizing a square matrix. So, again, this is just for your reference. If you ever kind of forget how to do this, you can look back to this. But basically, we start with again, it has to be a square matrix, an n by n matrix. The first step is to find those n linearly independent eigenvectors with corresponding eigenvalues. And if you can't find n linearly independent eigenvectors, then A is not diagonalizable. So obviously from that previous, from the prior theorem, you have to have n independent eigenvectors in order to be able to actually diagonalize A. All right, then the second step is P then is, again, the n by n matrix whose columns consist of those eigenvectors that you would have just found. And then the diagonal matrix D equals P inverse times A times P will have the eigenvalues on its main diagonal. Okay. So that's just the process of diagonalizing a square matrix. So let's go ahead then and take a look at an example and actually do this. So show that the matrix A is diagonalizable, then find a matrix P such that P inverse times A times P is diagonal. All right, so we're going to start by just finding those eigenvectors. So just like we always have, like we have in the last lessons and things like that, find the eigenvector, taking the determinant of lambda I minus A. So in this case, we would have lambda minus 1, 1, 1, -1, lambda minus 3, and -1, and then 3, -1, and lambda plus 1. Now, unfortunately, unlike a lot of the examples that we've done previously where there are a bunch of zeros, this does not have a bunch of zeros. So this one's going to take, unfortunately, a bit of work. So I'm just going to start in the upper left corner with lambda minus 1. So we're going to take lambda minus 1 and then times the determinant of kind of this lower part right here. So that's going to be lambda minus 3 times lambda plus 1, and then minus 1. And I'm just going to go across the first row, I think. So I'm going to go across now to this 1. We're going to look at this now. So minus, remember you have to do the plus, minus, plus thing when you're doing determinants. So minus, and now it's going to be technically 1 times the determinant of -1 times lambda plus 1. Minus a -3, so that's going to be a plus 3. And then we've got looking at the last one then, looking at this one, that's going to be plus. Now we're looking at this part, so we will have a 1 minus 3 times lambda minus 3. All right, so now we have to go through and actually simplify this whole thing. So let's see, we've got lambda minus 1, and then lambda squared minus 3 plus 1 is minus 2 lambda, minus 3 minus 1 is minus 4. Let's see, the plus makes this, or minus makes that a plus and a minus, so we're going to have plus lambda plus 1 minus 3, and then plus 1 minus 3 lambda plus 9. All right, so multiplying this out, we have lambda cubed. Let's see, minus 2 lambda squared and a minus 1 lambda squared is minus 3 lambda squared. We'll have a minus 4 lambda, and a plus 2 is a minus 2 lambda, and then plus 4. And then just doing some simplifying here, we've got a lambda minus a 3 lambda is minus 2 lambda. 1 minus 3 is -2, plus 1 is -1, plus 9 is 8, I believe. Yep. Okay, and then finally, lambda cubed minus 3 lambda squared minus 4 lambda plus 12. Now remember, we have to find the zeros of this polynomial. So this is the characteristic polynomial. We have to find its zeros, which we could do by factoring by grouping. If you remember how to do that, you basically, like in this case, we group like the first two, group the second two terms, pull out a lambda squared, pull out a -4, et cetera, et cetera. Honestly, at this point, just graph it. Just throw it into your calculator, throw it in an online graphing program, graph it and just find your x-intercepts, find your zeros that way. So in this case, if you do that, what you're going to find is that the zeros are, well, here, I'll do it this way. So the zeros are -2, 2, and 3. So x plus 2, or lambda plus 2, lambda minus 2, and lambda minus 3 is how it factors. And that's going to give us our eigenvalues. Lambda 1 is -2, lambda 2 is 2, and lambda 3 is 3. Okay. So the hard part is just getting through all that kind of algebra work of multiplying everything out and make sure you don't make mistakes. Simplifying, again, once you get it to that polynomial in standard form, graph it and just look at your zeros, look at your x-intercepts to get your eigenvalues. All right, we're still not done yet. Again, we're trying to show that A is diagonalizable. Try saying that 4 times fast. And so basically now we have to go through the process again of, for each of these eigenvalues, finding its corresponding eigenvector. So let's start with lambda 1 equaling -2. So in this case, we're going to take -2i minus a, and that gives us the matrix -3, 1, 1, -1, -5, -1, and 3, -1, -1. Now again, we want to reduce these down. So if we reduce this, we get 1, 0, -1/4, 0, 1. And obviously, this is something I just did on the calculator to get this. So, and you are certainly encouraged to do the same. But we get that final reduced row echelon form. And again, now you'd have your equations x1 minus 1/4 x3 equals 0 and so on. Set 1 to t, etc. Again, we should know how to do this by now, so I'm going to skip that step and basically just give you the eigenvector. So this is the eigenvector for lambda equaling -2, for the eigenvalue of -2. So this is our eigenvector. So moving on and doing the same for the other two, I'll show you the setup. I'll show you the same kind of work here. So for lambda 2 equaling 2, we would have 2i minus a. That's going to give us the matrix 1, 1, 1, -1, -1, -1, and 3, -1, 3. And again, just tossing this into your calculator, doing the reduced row echelon form, we get the matrix 1, 0, 1, 0, 1, 0, and 0, 0, 0. Setting up your equations and writing it out in linear combinations if necessary, you get the eigenvector -1, 0, and 1. And then finally for lambda 3, which was 3, we'll have 3i minus a, which is going to be 2, 1, 1, -1, 0, -1, and 3, -1, 4. And again, its reduced row echelon form is 1, 0, 1, 0, 1, -1, and 0, 0, 0. All right, so finally, its eigenvector, -1, 1, and 1. So again, this is stuff that we learned obviously in the last section. I'm just kind of assuming that you know how to do this by now, that you'd be confident with that from that lesson. If not, go back and relearn that in lesson 7.1. But now that we've got the eigenvectors, we can now set up our matrix P. So again, it's simply those eigenvectors that are creating the column. So 1, -1, 4, -1, 0, 1, and -1, 1, 1. Now, obviously, depending on the order that you do the eigenvalues in, that's going to change your P matrix. So, for example, I might have started with 3 and gone the other way. I might have gone 3, 2, -2, which would cause my columns to be in reverse order, and that's fine. So the order that you put this in doesn't matter. Just be consistent with your eigenvalues. So whatever you start with for your first eigenvalue, just make that the first column of your matrix. And so at this point then, this is a non-singular matrix. And I'm not going to go through the process of showing that, but it is non-singular, which means that the eigenvalues, or excuse me, the eigenvectors are linearly independent. linearly independent. And because the eigenvectors are linearly independent, and we have 3 of them for a 3 by 3 matrix, that tells us that A is in fact diagonalizable. So A is diagonalizable. Okay. So that was the first part, right? Showing that A is diagonalizable. Now it says, we already found the matrix P, but now we need to show that P inverse times A times P is diagonal. So very, very simply, and again, just go ahead and throw this into a calculator or some other software. But if we find this, we would find that we would get negative 2, 0, 0, 0, 2, 0, and 0, 0, 3, which of course is a diagonal matrix. Okay, now again, depending on the order that you put your columns into P, the order of those numbers in the main diagonal, so these 3 numbers, whoops, right here, they may be in a different order, and again, that's fine because it's just consistent with how you set up P. So don't worry necessarily about the order. Make sure that you've got the same values. All right, so now let's do one where A is not diagonalizable, and let's see what that looks like. So in this case, we've got A is 1, 2, 0, 1. Now, because this is triangular, right? This is a triangular matrix. We've got a diagonal of 1s, and then everything to this side is 0, which is really just the one value. We know that there's the eigenvalues are the entries on the main diagonal. So in this case, we just have one eigenvalue of 1. It just simply has multiplicity of 2. And so in this case, I just have 1 to check. 1 times I minus A, which is going to give us the vector 0, negative 2, and 0, 0. So reducing that very simply is 0, 1, 0, 0. So in this case, x2 equals 0. x1, because it's just zeros, can be anything, so we're just going to call that t. So in solving for x, finding the eigenvector, we would have t0, which is just t times 1, 0. So remember, trying to show that A is not diagonalizable, and in order to be diagonalizable, because it's a 2 by 2 matrix, we would have to have exactly 2 linearly independent eigenvectors. But in this case, we don't have that. We've got t times the vector 1, 0. So because A does not have 2 linearly independent vectors, eigenvectors, 2 linearly independent eigenvectors, we know that A is not diagonalizable. Okay, so that's just kind of what it would look like for something to not be diagonalizable, where you can't get exactly n linearly independent eigenvectors. All right, so that brings us to a theorem then that's a sufficient condition for diagonalization. It says if you have an n by n matrix A has n distinct eigenvalues, just like we talked about, then the corresponding eigenvectors are linearly independent and A is diagonalizable. So this actually simplifies a lot for us. If we go back, for example, and we look at example 4, so it says you've got a square matrix of order n, and it has n distinct eigenvalues, then we know that the eigenvalues are linearly independent and that A is diagonalizable. So if we go back to example 4, which had all this work that we had to do, where we had to show that A was diagonalizable, well, at the point that we found these 3 eigenvalues, A is a 3 by 3 matrix. We have 3 distinct or unique eigenvalues. By that theorem, it immediately tells us that because we had 3 distinct eigenvalues, that the eigenvectors are independent and that A is diagonalizable. Okay, So again, just to kind of see that one more time, determine whether matrix A is diagonalizable. Well, again, we've got a triangular matrix here. And so because of that, we know that the eigenvalues are just on the main diagonal. So lambda 1 is 1, lambda 2 is 0, and lambda 3 is -3. So again, because we have 3 distinct eigenvalues for a 3 by 3 matrix, then A is diagonalizable. So that theorem just really, diagonalizable, I can't talk and spell that word at the same time. So because of that theorem, it really does reduce a lot of the work if all we're trying to do is just show that a matrix is diagonalizable. All you have to do then is find the eigenvalues, and if they are distinct and equal to the order of the matrix, then you can stop right there and you know that it has to be diagonalizable. All right, so let's finish up with the way that we finished our last lesson. Let's look at diagonalization as it relates to linear transformations. And again, you're going to see a lot of similarities to what we just did here. So we've got a transformation T mapping R3 to R3, represented by the following equation. If possible, find a basis B for R3 such that the matrix for T relative to B is diagonal. Okay, so let's start by finding the standard matrix for T. And if you remember, this is where we take the equation or the rules for our transformation, and we simply create the matrix using the coefficients of those rules. So in this case, the standard matrix for T is going to be A equals, first row, I'm looking at this first rule, is just 1, -1, -1. Second row, now looking at the second rule, 1, 3, 1. And the third row comes from the third rule, -3, 1, -3. Or excuse me, -1. Okay, so that is our matrix. Now, before we go any further, because this is again where we'd have to go through all the work now of finding the eigenvalues, eigenvectors, which the eigenvectors, remember, are the basis, create the basis. So we'd have to go through all of that work, but we're going to shortcut this because if you look closely at that matrix, if I go back to example 4 again, that is the same matrix we used in 4. So all of the work we did in 4 would be the identical work that we would do here in this final example. We'd have to find the eigenvalues. We'd have to go through and find all the eigenvectors. Same thing, okay? So just understand that this is, if we hadn't done example 4, we'd have to go through all of this work in this final example, but we have everything that we need. And specifically what we need are the eigenvectors, because this creates the basis for R3, okay? So in this case, we're going to have then our basis is going to consist of the vectors 1, -1, 4, just pulling those from the top example, -1, 0, 1, and -1, 1, 1. So that is the basis B. So find the basis B. We've done that. And then just to show that the matrix for T relative to B, to that basis, is just the diagonal matrix, is just the -2, 0, 0, 0, 2, 0, and 0, 0, 3. So that would be the matrix for T relative to B, is just that diagonal matrix. All right. So that's kind of how we fit this into that idea of linear transformations. All right, well, that is actually it for this lesson. Again, just go back, review anything that may be confusing still, especially just work on and make sure you know how to find or know if a matrix is diagonalizable, all that stuff. So with that, I'll see you in the last and, believe it or not, final lesson for this course.